Hello, SPH4C. Here are the solutions to those homework questions that were part of the note. So let's take a look at question number 1. How much work is done on a 50 kilogram object that is pushed for 10 meters with a force of 20 newtons? So with this question, we know that the mass is 50 kilograms, the distance is 10 meters, and the force is 20 newtons. We're looking for the work, and in this case, the appropriate formula is work is equal to FD. So work is equal to 20 times 10, 200 joules. Question 2. Find the change in gravitational potential energy of a 15 kilogram object that is raised by 10 meters. So we know that the mass is 15 kilograms. The change in height is positive 10 meters because it's raised. We're looking for the change in gravitational energy. The change in gravitational energy is equal to mg delta h. So delta Eg is equal to mg delta h. 15 times 9.8 times positive 10, 1,470 joules. All right, let's take a look at question 3. Change of gravitational potential energy again. This time it's 20 kilograms and it's lowered from a height of 10 meters down to 5 meters. So the mass is 15 kilograms. My apologies, 20 kilograms. The initial height is 10 meters. Final height is 5 meters. We're looking for the change in gravity again, which is mg delta h. Eg is equal to mg delta h. But delta h is equal to m2 is equal to h2 minus h1. So that's 20 times 9.85 minus 10, negative 980 joules. All right, let's take a look at question 4. So this time we're trying to find the kinetic energy of a 1,500 kilogram car that is moving at 30 meters per second. So the mass is 1,500 kilograms and the speed 30 meters per second. We're looking for the kinetic energy. Ek is equal to 1/2 mv squared. Substituting in 675,000 joules. All right, let's take a look at question 5. Find the change in kinetic energy of a 1,500 kilogram car that decelerates, which means slowing down, from a speed of 35 down to 30. Mass is equal to 1,500 kilograms. V1 is equal to 35 meters per second. V2, 30 meters per second. We're looking for the change in kinetic energy. The change in kinetic energy is equal to 1/2 m V2 squared minus V1 squared. Substituting in 1,500, 30 squared minus 35 squared. Be certain that you calculate the bracket first, or when you put in your calculator, you make sure that the brackets are included. We should get a loss of negative 243,750 joules. So now let's take a look at the conservation of energy questions. Those are the last 3 ones. So here we have a rock is dropped from a height of 2 meters. What is the impact velocity? All right, so now what type of energies are involved in this one? So we say conservation of energy, which means that energy is going to go from one form to another. So in this case, we're talking about a rock being dropped from a height of 2 meters. So we know that gravity, this implies that gravity is involved. And since we're talking about impact velocity, that implies that we have kinetic energy as well. So those are the 2 things that we're going to be focusing on, gravity and kinetic energy. So first of all, let's take a look. We know that it's going from a height of 2 meters. It has to fall. So where does it land? On the ground. So we're assuming that it's a height of 0 meters. Now, the other key word here is it said dropped. That means that the initial speed has to be 0 meters per second because it's not thrown, it's dropped. So what we don't know is what the mass is. Okay, so how do we solve a particular problem like this? Well, what we're trying to find is we're trying to find the final impact velocity. So we're looking for the V2. Well, I know that the gravity formula is equal to mgh, and I know the kinetic energy formula is equal to 1/2 mv squared. So to get a good sense of this question, we're going to draw a diagram. So here's our rock, and there's the ground. So 1 is where it starts, 2 is where it lands. So our rock is falling in this direction here. Well, this is the information that we know. We know that the initial height is 2 meters, and we know that the initial speed is 0 meters per second. The final height is 0 meters, but the V2, well, that's what we're looking for. All right, so what we're going to use is conservation of energy. So based on conservation of energy, here's what I know. Is that the total energy at the bottom is equal to the total energy at the top. Well, let's take a look at the two energies that we got. So we have gravity and kinetic. So I know I have kinetic energy at the bottom plus gravity at the bottom is equal to kinetic energy at the top plus the gravity at the top. So here are the rules. If we have no speed, we have no kinetic energy. If we have no height, we have no gravity energy. So look at V1. V1 is 0 meters per second, which means that since initially it's not moving, that means there is no kinetic energy. It goes to 0. So that term cancels right out. And at the bottom, the height is 0. Since the height is 0, that means we have no gravity energy at the bottom. So then our equation becomes much simpler. It just becomes the kinetic energy at the bottom is equal to whatever the gravity was at the top. Well, now we put in our formulas. We got 1/2 mv2 squared is equal to mgh1. Well, we don't know what the masses are, but we don't care because since there's a mass on both sides, we can cancel them out. So now I'm left with 1/2 v2 squared is equal to gh1. So next step, I have to get rid of the 1/2. So I'm going to multiply both sides by 2. So if I multiply both sides by 2, this 1/2 cancels out. So we're left with v2 squared. And then if I multiply the right side by 2, 2gh1. Now I need to get rid of the square. Well, the opposite of square is square root. So I'm going to take the square root of the left side, and taking the square root of v2 squared just gets rid of the square root. And then I have to take the square root of the right hand side. So it's going to be the square root of 2gh1. Now we can put in our numbers. 2 times 9.8 times 2, 6.26 meters per second. All right, so let's take a look at our next question here. So this question, we have a 2 kilogram cart and it is propelled by a compressed spring. Okay, so when we see a compressed spring, that means we're talking about energy of a spring. If the spring has a force constant of 900 newtons per meter and it's compressed by a distance of 5 centimeters, how fast how fast will it move after the spring is fully released? Should probably fix that grammar. So this question, since it says how fast does will, or how fast will it move after, this is kinetic energy. All right, so let's make another GRFS. So first of all, we know that the mass is 2 kilograms. We know that the spring has a force constant of 900 newtons per meter. So K equals 900 newtons per meter. The spring is compressed by 5 centimeters. So it's initially compressed by 5 centimeters. Then the question asks, how fast does it move after the spring is fully released? Well, that means at the end, our x2 has to be 0 meters. Now, see how this says 5 centimeters? That's the wrong unit. We have to change it to meters. So that's going to be 0.05 meters. And the other thing that we know, and this is important, we have to assume that the initial speed is at rest. So the V1 is equal to 0 meters per second. So we're looking for the V2. Well, we have two formulas. The kinetic energy, 1/2 mv squared, and the spring energy, 1/2 kx squared. So here we go. Got a little diagram. So we got our spring, and then we have our cart. And this is what happens initially. So the x1 is 0.05 meters. Now, technically, I made a small little mistake. Technically, that should be negative because it's compressed. And the initial speed is 0 meters per second. Now, our spring is fully released and our cart is just moving along. So our x2 is 0 meters and our v2, well, that's what we're looking for. So before and after. Using conservation of energy, the total energy at the end is equal to the total energy at the beginning. So we have kinetic energy plus the spring at the end. It's equal to the kinetic energy plus the spring energy at the beginning. Okay, and here are the rules. Again, if the speed is 0, that means there's no kinetic energy. So since V1 is 0, E kinetic 1 is 0, no kinetic energy. And the spring can only have energy if the spring is compressed or extended. Well, here, since it's fully released, it's not compressed or extended, so there's no energy inside the spring either. So then we're left with 1/2 kx, let's try that again, 1/2 mv2 squared is equal to 1/2 kx1 squared. Well, since both sides have a half, the halves cancel out. I have to get rid of this m, so since it's m times v2, I have to divide both sides by m. So this is going to give me kx1 squared all over m. And then finally, to get rid of the square, we have to take the square root. So we take the square root of both sides, that gives me kx1 squared divided by m. So v2 is equal to the square root of 900 times 0.05 all squared divided by 2. And we get 1.06 meters per second squared. And finally, the last question. Wile E. Coyote is running through the New Mexican desert when he randomly runs into a massive elastic band. Okay, so elastic band, that's a clue. That's going to be spring potential energy. Also a clue, it says spring. And it has a spring constant of 20 newtons per meter. If the spring compresses a total of 10 meters, how fast was he going? Okay, so now this case, things are a little bit different. So we know that fast has to do with kinetic energy. So in this case, he was running first, then he ran into the elastic band. That means he's going from kinetic energy to spring energy because the spring is going to stop him and take away his kinetic energy. All right, well, let's write this all down. So let's copy another one of these. All right, so now, what do we know? So first of all, we know the spring constant is 20 newtons per meter. Next, we know that the spring compresses a total of a distance of 10 meters. But that's after, which means that initially the spring wasn't compressed, or the elastic, I should say, wasn't stretched. So we have to state it as x1 is equal to 0, otherwise we won't have that information. And our x2, 10 meters. And finally, we know that the final speed has to be 0 meters per second. So what we're looking for is the initial speed. All right, so we know that the energy of the spring is equal to 1/2 kx squared. Kinetic energy is equal to 1/2 mv squared. Well, we don't really need a diagram for this one. I mean, we could make one, but we're not going to. We're just going to go right into it with the conservation of energy. So in this case, we're trying to find the initial speed. So I'm going to have ET1, the total energy at the beginning, is equal to the total energy at the end. So that's the kinetic energy plus the spring at the beginning is equal to the kinetic energy plus the spring energy at the end. And again, let's remind ourselves, things cancel out when things are 0. So for example, the spring, or the elastic I should say, is not being stretched yet. So there is no elastic energy in the elastic band at the beginning. And at the very end, Wile E. Coyote comes to a stop, so the kinetic energy is 0. So we're left with the initial kinetic energy is equal to the final spring energy, which makes sense. All of Wile E. Coyote's kinetic energy goes into the spring. Okay, so the halves cancel out, and we have to isolate for V1. So I'm going to divide both sides by m. So I'm left with V1 squared is equal to kx2 squared divided by m. I got to get rid of the square. The opposite of square is square root. So I take the square root of both sides, and I'm left with kx2 squared over m. So we made a small little oversight, as in I made a small little oversight. There's one critical piece of information that we don't have, and that is, what is the mass of Wile E. Coyote? So we're going to have to go on the internet and look that up. And this was a mistake. What is the average mass of a coyote in kilograms? So 8 to 20 kilograms. So let's split the difference and say 14 kilograms. We'll add that. Mass equals 14 kilograms, which would work out to an astounding 80 meters per second. Now that is cartoon physics. That would be very fast. I think I may have to fix this question. But anyway, that's how you solve it with the wrong way that I've written it. Anyway, that's it.